The next step is to simply verify that the preferred mate actually occurs in our population. So if any of these entries are 0, they can't be a mate. And here we'll use an HLOOKUP function. Let's find that. It really will be an if function with another HLOOKUP function included, but we'll start with the if function first. So let's find HLOOKUP, and H stands for horizontal. And what we're doing is we're looking up the preferred mate in a table. And our table is going to be cells J2 through L3. We'll anchor the reference to that. And the H means that this value we're looking up must be in the very first row of the table, the first horizontal row. We want to look into this table and return the second row associated with that. So that row index number is number 2. And the range lookup here is a true-false entry. If we want an exact match, we enter the word false. So what this is doing, this HLOOKUP function, is just looking up the number of A1 individuals and returning it. So if I entered A1A2 in cell E15, it should return the number 500. We want to know if this is at least 1. So we're going to embed this HLOOKUP into an if function. And we'll say if this HLOOKUP result is greater than 0, then we'll just return the preferred mate. Otherwise, we'll return a missing value, and we'll indicate that with a period. We'll close the parentheses and then copy this formula through. So here now we have our parent's genotype, we have their preferred mate, and we have their actual mate. And the actual mate, once again, is just to ensure that that individual genotype is present. Now what that means is if there's just one individual and the entire population wants that genotype, that one individual will have many opportunities for mating. The next step is to simulate the process of meiosis for both parents. And we'll use the same equations we did in Hardy-Weinberg. So for the parent, we'll draw a random number, and if the random number is less than 0.5, we'll return this allele, this gamete. The gamete will contain this A1. Otherwise, it will contain this A1. And we use the left and right functions to do that. Let's find the if function. And the logical test is going to be a random number is less than 0.5. If it's true, we want to return the left 2 digits associated in cell C15. So we'll enter left and then comma 2. Otherwise, we want the spreadsheet to return the right 2 digits, and we'll write right C15 2. So that is intended to simulate the process of meiosis, the process of forming sex gametes so that this particular cell and the sex cells have just one gamete, and then those will be joined when the actual reproduction occurs. The mate's gamete will be calculated similarly. So let's do an if function there. If a random number is less than 0.5, we're going to return the left 2 digits, or 2 characters, from cell F15. Otherwise, we'll return the right 2 characters from cell F15. The offspring genotype then, in column I, is just the joining of those two gametes. And we can use the concatenate function or just enter the AND symbol to join those two. In column J, we'll simply return the offspring genotype, and we have two issues to deal with. The first is we only want to produce offspring if the parent is in the count. And second, we want to flip the genotypes that are listed as A2, A1 and change those to be A1, A2. And that, remember, is because the spreadsheet can return a heterozygote and list the heterozygote as either A1, A2 or A2, A1. So let's handle both of those problems in cell J15. We'll use two more if functions, which is the function of choice for this exercise. The first is going to be if the count is equal to 1. If it's not equal to 1, then we don't want to return a genotype, and again we'll use the two double quotes. If it is equal to 1, though, now we need to determine if the offspring's genotype is equal to A2, A1. And if it is A2, A1, we want to turn it to A1, A2, so that we have just one kind of heterozygote represented. And if it's not A1, A2, we simply want to return the value that's originally stored in cell I15. And we should be able to copy this through. And now we have an offspring population that we can compute some outputs with. We need the genotype numbers, the genotype frequencies, and the allele frequencies. So put your video on pause, enter those equations, and then we're most of the way done. We're at the point then of being able to calculate our observed and expected heterozygosity. The genotype numbers of our offspring population is going to be calculated with the COUNTIF function. The range in this case is the genotypes listed down column J, and the criteria is going to be the value stored in cell J2. Let's anchor the range and copy that through. You can see that already we're seeing some deviation from Hardy-Weinberg expectation. The genotype frequencies then are going to be simply the number of individuals of each genotype divided by the total. And that reference to the total needs to be fixed. So again, we are making a simplifying assumption here that each individual that is present in the parental population produces just one offspring. And let's take a look at what happens here. We can see that we've changed the genotype frequencies from time step t in blue to time step t+1 in red. We started off with a genotype frequency of 0.25 for the A1A1 homozygote, 0.25 for the A2A2 homozygote, and 0.5 for the heterozygotes. And through this mate choice grid, in the next generation we have depressed the frequency of the heterozygotes and have increased the frequency of the two homozygote populations. Now let's calculate the frequency of the A1 allele. That's going to be 2 times the number of A1A1 homozygotes plus the heterozygotes divided by 2 times the total population size. And we'll put each of those terms in brackets, the numerator and the the denominator to ensure that we follow a standard order of operation. And we'll do the same for the A2 allele. That's going to be 2 times the number of A2 homozygotes plus the number of heterozygotes divided by 2 times the population size. And you can see that when you press F9, you're generating new random numbers each time. And each time we're updating our allele frequencies as well as our genotype frequencies. Now let me press F9 a few times and tell me what you observe. If you look at the two graphics, you should see that the allele frequencies are not changing through time. They're staying relatively the same. A1 starts off with an allele frequency of 0.5, and through this non-random mating, we're really not affecting the frequency of the A1 allele. So what are we affecting? Well, we're affecting the genetic diversity. We've decreased the number of heterozygotes, or decreased the heterozygosity of the population. And that's one of the key things to keep in mind with respect to non-random mating. Now let's get to the final portion of our spreadsheet where we calculate the observed heterozygosity and the expected heterozygosity. The observed heterozygosity is going to simply be referencing what you observed in cell K9. What would you expect under Hardy-Weinberg equilibrium? Well, if you remember from Jed's video, that's going to be 2 times the frequency of the A1 allele times the frequency of the A2 allele. And this will be from the parental population. The parental population starts off with 50% of each allele. We expect the heterozygosity. We're going to reach into the bag, pull out an A1 and an A2 allele, join them together. There are 2 ways to create that. That's why we have the number 2 there. And we end up with an expected heterozygosity of 0.5. So you can see this is a clear indication of what non-random mating is doing. In this particular case, if with this particular choice grid, we're observing 30% or 29% of the population with a heterozygous genotype, whereas under Hardy-Weinberg we expected 50% of the population to be heterozygous. And now we can calculate the F statistic. Remember what that was? That's going to be what we expect under Hardy-Weinberg minus what we observe. So that tells us how far are we from the Hardy-Weinberg expectation, and then we're going to divide that by the Hardy-Weinberg expectation itself to just sort of put us on the same footing no matter what we start with. And we'll see that our F statistic is 0.43. So it's someplace down here. So this is representative of not a fully inbred population, but it certainly indicates that the population is not randomly mating. And to give you a sense of what these F statistics means, we've entered input cells in cell P8 and P9 where you can enter whatever it is that you'd like. And the F statistic would be calculated and can show you where you are with respect to observed and expected and how the F statistic is computed. So remember, if they match perfectly, then we have a case of random mating. If the heterozygosity is lower than what is expected under Hardy-Weinberg, then we move up to the inbred indication. And if we observe more heterozygosity than what is expected under Hardy-Weinberg, we then move up the scale to a condition where outbreeding is occurring. So that, in a nutshell, is the inbreeding spreadsheet exercise. And we'll be playing around a lot with this exercise in the sandbox, where we'll be able to really change this mate choice grid and see how that affects our outcome. We'll also be able to determine if population size has anything to do with affecting the outcome. And further, we'll be able to run a macro that will let us calculate this F statistic through time and see how it changes if we have a mate selection choice that is constant through time. So now we'll head back over to Jed and we'll review some basic concepts of why inbreeding is so important from a conservation perspective. So Jed, it's back over to you.
Great. Thank you very much, Terry. I hope you found that spreadsheet exercise helpful in terms of understanding what inbreeding is, what outbreeding is, how it affects populations specifically at a genetic level. So we've covered a fair amount of ground in this module, and to recap, let me cover a few of the key points. At Hardy-Weinberg equilibrium, among a population, we assume that there's random mating occurring, random mating among individuals in that population. But we know in nature that non-random mating occurs quite regularly. In fact, in some places, some species and situations, it seems to be the dominant paradigm. And that non-random mating can result in some cases inbreeding and in other cases outbreeding. So those are two forms of non-random mating. In the case of inbreeding, we have that occurring when individuals, mated pairs come together that share genotypes that are more similar than what you'd expect if they had mated at random. And inbreeding has a specific consequence. It typically results in lower amounts of heterozygosity within that population. Outbreeding now is the opposite. It's sort of the flip of that. And in outbreeding, we have individuals, mated pairs coming together that have genotypes that are less similar than what you'd expect if they had mated at random. And that also has the opposite effect of inbreeding. So the specific effect it has in terms of the genetic makeup of a population is that it increases, not decreases, the amount of heterozygosity. Sometimes inbreeding and outbreeding can have negative consequences for individuals. It can have depressing effects on fitness. It can reduce fitness, and I mean biological fitness here. When that happens, we refer to that situation as being inbreeding depression or outbreeding depression. Now we can estimate the extent of inbreeding or outbreeding or the extent of non-random mating in a population by calculating something called an F statistic. And in order to estimate an F statistic, we're essentially comparing a population that we would, the values we would expect at equilibrium, at Hardy-Weinberg equilibrium, and we would compare that to what we might observe in that population. And so this F statistic, or this inbreeding coefficient as it's sometimes called, gives us a value from 0, 1 that in some ways indexes the extent or the magnitude of inbreeding or outbreeding occurring in a population. So I hope at this point you've got a pretty good understanding, a solid understanding of what inbreeding and outbreeding are, how they affect populations at a genetic level, and how they might be relevant to species management and conservation.